I'd like to say a very warm welcome to everyone. Thank you for taking the time to attend this Rise Masterclass today. My name is Nikhil Vaswani, and I am a junior consultant at Turner and Townsend. And today we're kindly joined by Julian Boss, a principal consultant at Turner and Townsend. The purpose of this event is part of a retrofit information, support, and expertise event, which is fully funded by the Department of Energy, Security, and Net Zero, and is delivered by Turner and Townsend. Thank you very much again to everyone for joining. I'll shortly share those links in the chat, and without further ado, I will now hand it over to Julian to start today's presentation. Thank you. Julian, over to you.
Thanks, Miguel, and welcome everybody to this Rise Masterclass. And we'll just proceed straight onto our agenda. So basically, yeah, we're looking at obviously fabric first and no regrets. I don't know if you've heard of these terms before, but fabric first is an approach which is all about looking at the fabric of a building in terms of improvement as part of retrofit. This is also the approach kind of reinforced by PAS 2035, and no regrets is a sort of, again, a bit of an approach really thinking about the whole house retrofit and not doing single measures ad hoc according to maybe funding or some other kind of encouragement that really means that you're doing improvements out of what would be a natural sequence, and so that you're in effect blocking further retrofit down the road. So you're kind of following a sequence that's normally outlined in a medium-term retrofit plan, which is part of the PAS 2035 process. So worst first is also looking at the same thing, really addressing the kind of serious issues that are part of the retrofit assessment and highlighted by that process, as opposed to, again, just doing measures as and when funding becomes available to do those measures. It's got to be part of a proper strategy. And then finally, just thinking about other resources that RISE can provide. So we'll kick off. So the key principles really around what PAS and I suppose a national retrofit approach is all about reducing the heat loss. So ensuring heat loss prevention measures are installed before other energy efficiency measures in order to maximize suitability for low carbon heating. So basically, looking at that fabric, looking at what we can do to the different elements, the roof, the walls, windows, doors, floor, obviously thinking about proper ventilation as well when we're improving air tightness of our leaky old buildings. So we need to ensure good ventilation, maintaining that indoor air quality. And also, second point there, minimizing the potential for measures having to be replaced in the future. And that generally with our fabric measures, they do tend to have a longer lifespan than boilers and other heating appliances. They tend to, the fabric measures like insulation and windows tend to be sort of certainly, you're looking at tens of years. Wall insulation, 25 plus, windows certainly 10 plus, and really the heat and boiler replacements are around about that, but can be shorter. So we're all obviously thinking about how the fabric improvements and money spent on that will outlast any kind of improvements to the heating elements of the building. So yeah, two key principles to bear in mind. So just thinking about the net zero targets, government target of net zero by 2050. This obviously means net zero carbon, and the approach is very much thinking about how do we reduce the energy demand of our homes as much as possible, and then switching to electricity, because obviously we're getting rid of fossil fuel burning appliances, cooking and heating, and then providing that electricity as low carbon. So those 3 points there really kind of the underlying approach: reducing heat losses by improving building performance of fabric, and reduce other energy uses in homes through improved efficiency, and then delivering our energy from low carbon sources. So thinking about obviously nuclear, renewable, and in future hopefully maybe tidal as well, but wind, solar, nuclear, and potentially wave and tidal stream as well in the future. So just thinking about the relative impact of homes in terms of overall carbon emissions, between 15 and 20% of the UK's carbon emissions come from energy use in the home, and our boilers account for around about 60 to 65% in terms of space heating and water heating. The rest is coming from use of appliances, such as washing machines, kettles, cookers, fridges, freezers, you name it, vacuum cleaners, hair dryers. There's lots and lots of different things in there which use power from motors or heating or cooling. And of course, lighting, though, since the introduction and widespread availability of LEDs, that's reduced dramatically. We do have some enhanced construction standards around building regulations, which are ensuring that new buildings are increasingly energy efficient. But the legacy building stock, around 26 million homes, so that number does vary between 28 and 25, depending what you read, has relatively poor thermal performance, and over 90% of the existing housing stock is expected to still be in use by 2050. So that this really is the big area of carbon reduction which needs to be addressed. So even if we could replace the buildings and that was seen as desirable, the cost is unaffordable, and the carbon emissions associated with that demolition and reconstruction would also be considerable. On the graph here, some of these you can see have reduced significantly electricity supply. So this is obviously the effect of removing coal and adding all the onshore, offshore wind and solar that have been put in over the last 35 years, sorry. Other areas, we're looking at this sort of blue-grey line here of industry. So we've probably associated a lot with the electricity use within industry. That has come down as well. But we can see in the various other areas, such as surface transport, obviously, lorries, cars, etc., has changed somewhat, I suppose, reduced by the introduction of electric vehicles, but it's still a small proportion. And our buildings have come down a little, but again, we need to be addressing this in a much more aggressive manner. So just looking at the kind of way that heat demand has been addressed, and what it is that we're kind of talking about. On the columns here on the left, the dark blue-green color here, you can see that basically 1900s, all those lovely solid wall properties that were built around that time, the heat demand of those properties was pretty significant. It wasn't the primary concern of those buildings at all. And obviously they were, using plentiful coal supplies at the time. Every room practically had a fireplace. And we can see that obviously moving along to when after building regs have been, significantly established, and the kind of introduction of proper energy efficiency standards was reducing the new build down to just over 100 kilowatt hours per square meter per annum. And that's been steadily reducing. The overall UK average is this here, the orange column, obviously taking into account our quite significant amount of period properties that are still being lived in. Some of the kind of indicative retrofit trials properties that we're looking at probably about 40 kilowatt hours per square meter per year. The trial properties and the pilot properties do tend to be pushing that performance very significantly. And obviously, when we're thinking about SHDF, we've had targets of 90 kilowatt hours, certainly for wave 2.1, and I think 2.2. I'm not sure that's been in, I don't think it's not in the draft guidance for wave 3. But anyway, it has been a target, certainly within SHDF, but we can see that these retrofit trials have been significantly below that. Best practice that you're really talking about NFIT, so that's passive house retrofit standards, and that's 25, that target. If you can actually retrofit to a passive house standard, that is 15, which is down here on the right. We can see here the various upgrades of building regs more recently have been reducing this, but as we said, the impact of new build on all of this is tiny, less than 1% per year of replacement homes. So just thinking about the energy use within the home in terms of its sort of proportions. So heating and hot water, as we said, were sort of 65% on this pie chart. And then we're thinking about appliances, lighting, cooling on average, and then other, which is, vacuum cleaners, dishwashers, washing machines, microwaves, hair dryers, kettles, things which, only get maybe used for a relatively short time, but they're high energy use and they are significant. And just thinking about the heat from that sort of crimson colored sector, heating 44%, where does that go? And it's basically as it's leaving the building, this is how that leads through the fabric. So we're looking at, walls 35%, roof 25%. That's the main bit. And then drafts and windows and doors is another 25%. Floor 15. Again, these are very average, figures, and it gives you an idea of why we are always thinking about these measures as the primary areas to address in fabric. Again, reiterating that you do have to do all of this with a very, very keen eye on ventilation and indoor air quality. So just thinking about what is fabric first, it's the external envelope of the building. So whatever the scale of retrofit, a technically sound and usually cost-efficient approach is the one known as fabric first, which should always be considered when a retrofit plan is formulated. Existing building fabric should be as energy efficient as possible before spending resources on other measures. Subsequently, because insulation measures are generally amongst the most cost effective and long lasting, as I mentioned earlier. And actually that would indicate probably the best investment. Insulation is usually the most appropriate next step. Insulating the fabric also reduces the required capacity and cost of the heating system. So if we're reducing the relative heat loss from that building envelope by 20, 30, 40, 50%, it has a big impact on the heat production of whatever heating system you're putting in. It shifts the bias away from the space heating to the hot water production as being a more important factor. As I said earlier, heating system usually has a shorter lifespan than the improved building fabric, typically about 15 years compared to up to 60 years for the fabric. So the dwelling might have 4 heating systems during the life of the installed installation. Low and zero carbon systems such as solar water heating, otherwise known as solar thermal. Photovoltaic systems are normally the final step because they're relatively expensive and often required a subsidy, and their capacity obviously limited by available space. Most UK dwellings cannot be heated exclusively by renewable energy systems unless they're first insulated and the building service's efficiency is improved to reduce the remaining energy demand so that low and zero carbon systems can make a significant contribution. So just thinking in a bit more detail about what the fabric first approach is really talking about. So here we can see in a sort of diagrammatic form the structure of the building, lifespan about 50 to 100 years. Then the outer skin is 25 to 50 years. So talking about render, pointing, brickwork, it could be shuttering, it could be all sorts of different finishes that are on the outside of the building. We've got the building services, which are 15 to 25 years, and the space planning, 5 to 15 years. So just thinking about how often we have started to invest in these different parts of what we would think of as a home. And then the stuff inside, obviously our belongings, for up to 5 years as an average, though not the case in my house. So what we're thinking about here about the danger of locking in mediocre improvements is really about what I said earlier about understanding about what a proper whole house retrofit plan would be, and if you're doing this incrementally, what are the first? How do you understand the steps you take and in what order, so that you don't jeopardize future retrofit work? I won't go into that graph right now, but you'll be able to look at that when we share this with you. So fabric first, it's really thinking about these elements: continuity of insulation. So there's that insulation layer around the building. Obviously, this is an external layer. Just looking at this, external to the wall structure. Though, if it was a cavity wall, your insulation layer would be within the cavity. If it's a listed building, the insulation layer would be likely inside the wall. The conservation area, it might be inside the wall at the front, so the frontage onto the street, and you could do an external outdoor external wall insulation at the back. Hybrid system, that's called. So we have a continuity of insulation, no thermal bridges. So thinking about areas where you have the junction of the wall and roof, this tends to be an area where you have maximum heat loss. Oops, sorry. And that needs to be addressed with a proper detailing of the insulation. Tends to be around these corners. So you've got the floor to walls, roof to walls. Around windows, there can be cold bridging. So you need to be careful about positioning of windows, that kind of thing. Obviously, good quality components. We're thinking about reliability over the long term, adequate ventilation. And in this case, it's got a heat recovery ventilation system. So supplying air into living areas, extracting air from cooking and washing areas, which tend to be the most elevated levels of moisture. And the heat recovery unit basically captures the heat in the waste air going out and uses that to pre-warm fresh air coming in. And on this we're talking night purge ventilation is basically at night when temperatures are acceptable. You just can open windows to allow the air to replace itself across the dwelling. Good air tightness is really thinking about minimizing the draft. So what's also called uncontrolled ventilation, creating a draft-free home. And obviously, when you do that, you're what's called maybe a background ventilation, natural ventilation of the house is basically air that is passing through due to cracks and holes and gaps around pipework, gaps around windows and under doors and that kind of thing. But if you added all those cracks and gaps up, you would probably be getting close to, a square meter of just open space over the whole house. And if you were to do that in the middle of winter, you'd obviously notice it. So yeah, we do need to be thinking about draft proofing and then providing proper ventilation. So thinking about it, the scope of works for Fabric First really is kind of a summary of the things we've done, but things we've looked at, but also with things like windows and insulated walls, you do need to be very aware of, and this is down to the retrofit designer, positioning of those windows within the insulation layer. So if you do have a Windows program going on and then you're going to do EWI, it's kind of best to do them at the same time if it's possible, because you need to be able to move the windows into the insulation layer in order to really minimize the cold bridging. You can get some very interesting heat loss pathways around windows, as I said, if the insulation is all on the outside and actually it provides a pathway right round the window, the whole window frame, unless you have careful detailing of the insulation. No regrets. Really thinking about that kind of retrofit strategy, and these points, I suppose, do summarize the risks or regrets. So unplanned improvements can result in current retrofit measures being removed to enable future upgrades. So that's why I was saying don't do things now which will later hinder further retrofit work. Unplanned improvement can result in inadequate ventilation and or cold spots, thereby increasing the risk of condensation, mold growth, and reduced air quality. Absolutely, your cold bridging, cold spots can be a magnet for condensation, especially if you've reduced the background ventilation, haven't provided adequate ventilation after the retrofit. You've still got all your moisture in the air and it just is drawn to all the cold bridged areas, and you get some pretty shocking mold growth in those areas if you're not careful. Unplanned improvements can lock in mediocre outcomes, making future decarbonisation more difficult. Again, you can create it without planning this properly. You can end up creating all sorts of unwelcome, unplanned other impacts unforeseen consequences, really, which is that you suddenly end up with a bigger problem than maybe you had before, which might mean having to move people out of a home to remedy that, and suddenly you're having to spend a lot more money on works which you hadn't anticipated in order to sort out problems that have happened because of this unplanned improvement process. It needs to be carefully thought through if you're going to avoid that kind of thing. So this, if any of you have seen any of the versions of PAS 2035, and this is the retrofit measures interaction matrix. It's basically a tool to indicate which measures don't interact negatively. So the green squares here are basically saying all the measures which have a green indicator don't interact and they're fine to go in together. Where you have yellow, that's where they're connected physically. Orange, they can interact in other ways, and red, they are incompatible. So a kind of quick indication that, when people are considering certain measures in here, that'll give you a very quick idea to not consider putting them together if they're on red. And amber and yellow generally are to proceed with caution, really. So this is just a quick slide summarizing the roles that are now part of the PAS 2035 retrofit process and really thinking about their responsibilities. So there are 5 roles defined in PAS 2035 and all play a part in ensuring good quality retrofits that help meet their intended outcomes and reduce risk of unintended consequences. Some of these roles can be performed by the same individual if they have appropriate qualifications. However, retrofit evaluation should have a degree of independence in order to provide a truly objective view of overall project performance. But for instance, if someone was a qualified architect with good experience around buildings, they might easily qualify as a retrofit coordinator. They'd certainly be a retrofit designer. They'd certainly probably understand retrofit assessment. It's probably better to have separate people in these roles, but depending on the project, that might not be possible. Obviously, an installer is likely to be part of a contracting company where they have a certification, PAS 2030 certification, for a particular retrofit measure. A retrofit assessor, so actually I suppose I should summarize these quickly. You can see the notes there, but we'll just run through that. So the retrofit coordinator is a kind of project manager for the project, but it's really from the start to the finish, and their responsibility does begin really from the outset, and they would appoint the retrofit assessor to do that first kind of piece of work around a survey of the home, assessing its suitability for retrofit, finding any underlying issues, etc., etc. But the retrofit coordinator really has responsibility all the way through. They are making sure that the whole process is being followed, the PAS 2035 process is being followed, that the data about the project is being lodged with Trustmark and in the data warehouse. They're checking the certification of individuals involved in the project. They are basically ensuring compliance the whole way through the project. So the retrofit assessor, they would be doing, as I say, that assessment survey of the existing property. They're also producing a kind of indicative EPC type of assessment as well. It's not an EPC that would be lodged with the EPC register, but it gives a kind of before retrofit rating. They're normally a domestic energy assessor, a DEA, and can have further training on retrofit as well. The retrofit designer needs to have appropriate qualifications. That's outlined in PAS 2035. And that could be, as I said, a building professional or an architect, suitable again for the project, and they will provide a detailed design. If it's for single measures, then that could be a design or a building professional trained in a particular system. But again, this is down to the retrofit coordinator to know what is appropriate for that project and to be appointing the designer that has the right qualifications for the kind of complexity and risks around that particular project. But the designer is really there to ensure that the correct materials and products and detailing are specified for the retrofit, the measures rather. So it's the measures which would include different, types of insulation, finishes, and it could be a product as well. And actually the detailing around, as I said, cold bridging is a particular high risk area. So the designer will be the person who's specifying the detailing around those high risk areas. The retrofit installer is the contractor who's there to install the specific measures, and they'd be certified to PAS 2030 for the measure that they are installing. And then the retrofit evaluator, they would be basically coming in to do the monitoring and evaluation. And although this is at the end of the process, it does need to be considered at the beginning, depending on the complexity of that project. So where does the retrofit go wrong? Here are a few images on the right of the kind of things we want to avoid. So these are certainly, a lot of these images are around where you've got horrendous mold growth because of cold bridging, poor ventilation, high levels of humidity, etc., etc. Very poor detailing here around at the bottom of this insulation. And it looks like some sort of unresolved issue of some kind where rising damp or penetrating damp is affecting the wall finish there. Could be for all sorts of reasons. Could be a pipe, it could be rainwater goods outside, could be a mains pipe, or a damp-proof course that's broken down. It does look quite localized, that, so it could be something quite specific. Anyway, so just thinking about these areas. So really we're thinking about the interaction risk, so corners, junctions and edges, as I said, where you can get kind of water penetration, thermal bridges around those junctions of the elements, thermal bypass, which can happen around insulation, where there's too much of an air gap between the insulation and the thermal element, and air is allowed to move and it basically bypasses the thermal properties of the insulation. Joist ends, this is a risk basically where moisture can cause rot in timbers when they're embedded into a wall. There's nowhere for the moisture to go, which ends up finding its way to the end of the timber. And is a high risk of that timber rotting, and therefore you've got structural issues. The next one on there is about the interfaces. So this is really interfaces between the building fabric and the surfaces. So you have air tightness, obviously thinking about the draft proofing, and weather sealing around pipes, and anything that penetrates the fabric of the building. So it can be pipe work, window openings, door openings, wires, anything that's penetrating that layer that needs to be sealed and have the right sort of airtightness products. It can be foam strips, it can be silicons, it can be gaskets and grommets and all sorts of different things that can be used, but they all need to be used because, as I said, when you add up a few of these things together, you end up with the equivalent to quite a significant hole, which is allowing cold air in and or warm air out. So also thinking about those handovers where you've got the resident who's now living in this retrofitted home, maybe with new controls for their heating system or even a new heating system, possibly ventilation systems as well. So it could be a single room ventilation with heat recovery. It could just be background ventilation with a boost facility. It could be all sorts of things. They don't necessarily need to, they might not, through the handover process, understand how these things work and might think there's something wrong because they're on all the time and therefore they switch them off. They might regard them as too noisy. In most instances, they're no more noisy than, a fridge or something like that. The other problem is poor maintenance. So if maybe filters need to be changed or certain elements need to be cleaned and regularly serviced, then that can make a big issue on the performance. So again, thinking about the no regrets elements, the importance of accurate measurement. So this is really to do with understanding energy use. And actually, we do hear about SAP and, well, particularly RD SAP being a difficult thing to base energy use on. RDSAP is really an energy model which is used to generate EPCs, and it makes certain assumptions along the way, and these might not reflect the real performance of a dwelling with a particular level of occupancy rather. So that's all to do with, preferences for indoor temperature, preferences for amounts of cooking, amounts of washing per week, etc., etc. So we need to understand how much moisture is being potentially generated into the indoor space through cooking, washing, occupancy levels. These all affect the levels of humidity, and really they dictate the levels of ventilation performance that you need in order to maintain good quality indoor, not have this risk of extremely high levels of moisture, humidity in the air, which are a risk in terms of condensation and mold. And that second point is really thinking about accurate energy modeling. So PAS recommends SAP, full SAP, or PHPP, which is the Passive House Planning Package, as better tools to use for the energy modeling. So just a brief word about worst first. If we look at these two buildings are right next to each other, and you can see the condition of the building on the left, which is basically what the retrofit on the right was addressing. You can see by the shadow at the bottom of the brick line on the right-hand building that layer is an insulation EWI layer with a brick slip finish to basically do a pretty good job of imitating the finish on the terrace. And basically, it's got double glazed windows that have been set into the insulation layer. You can see that they are not set back in that insulation layer. They've been brought forward, so that looks like pretty good practice in terms of minimizing the thermal bypass, cold bridging around the window frames. The rainwater goods will have been moved out as well. I can't really tell from the detailing the roof line there, but obviously that would need some good detailing between the roof and the top of the external wall insulation layer in order to minimize the risk of water ingress, water getting behind that insulation layer. It looks like you can see that white line here. Looks like a kind of finish, some kind of flashing along the top of that insulation layer. Oops, didn't mean to do that. But anyway, we're moving on to the resources. So just thanks for listening to the presentation. We have these presentations on the RISE website, and lots of other resources relating to the issues around the retrofit design and obviously around the application process for various government-funded retrofit programs. Obviously, FWAVE 3 would be one of the current ones, but there's going to be others coming, I'm sure. And the RISE website is really catering for future waves of funding, all relating to different parts of the retrofit process.